Okay, from the equation 1 prime, from this equation, the slope is simply given by the coefficient of VD, since it's the slope is negative, which is why the line is inclined the following way. So the slope here is simply -1 divided by R. So that is my constraint that relates VD to ID. And where did that constraint come from? That constraint is the constraint on ID and VD that has been imposed by the rest of the circuit. So if the first constraint was imposed by the device, then the second constraint is imposed by the Thevenin equivalent that is connected to the device. Okay, the Thevenin equivalent was the V and R in series, and those two impose a Thevenin constraint on the terminal pair that relates to VD and ID. So now my next step is given these two graphs for ID versus VD, and clearly those are my two constraints. The graph 2 says that ID and VD must be somewhere on this trajectory. Graph 1 prime says, well, I'm not going to let VD and ID be anywhere else but on this curve. Okay, that's it. Both of them are fighting against each other and telling each other, nope, I'm not going to allow you to do anything. You have to be on my curve. So in this case, I have two curves, and I need a point that satisfies both curves. And that is easy enough to do. And I simply have to go and satisfy both these constraints, and that will give me the answer for VD versus ID. Before I do that, so I can go and solve it for you, let me go and pick some values for the various parameters. So as before, I'm going to pick V equals 1 volt, R equals 1 ohm, a quarter of an amp, and B to be 1 volt inverse. Okay, so I'll pick the same parameters as I had done in the when I did the analytical method. Next, what I'll do is I'll substitute these parameters into the two equations, 1 prime and 2, and rewrite them with the parameters substituted. So for 1 prime, I get ID. Since V is 1 and R is 1, I get V divided by R equals 1. And then since R is 1, I get minus VD. So this is 1 prime, once I've substituted the values. And then for equation 2, what do I get? I get ID equals AE raised to BVD. A is 1 quarter, so I write that down. B is 1, and so I get VD up here. So I have my two equations in terms of the parameters I've chosen, and now I can go ahead and plot the two equations and see where they intersect. I've given you the form of the graph here, and so let me go ahead and plot this. Let me go ahead and plot 2 first. 2 looks like this, where this point is 1/4. That was the A point. This curve, as I said before, this curve is simply my equation 2. Then let me go ahead and plot equation 1 prime, and as you recall, that looked something like this, where the VD intercept was V, and the y-intercept was given by V divided by R, and in this case it was 1, and V was also 1. So those are my two curves, and here's the intercept. Here's the point where the two coincide. And then I just have to go and find the values of ID and VD where they do intersect. So this point will be 0.56 volts, and this point will be 0.44 amps. Okay, it's the same as what I calculated in the analytical method. And so let me go ahead and write that down. ID equals, in this case, 0.44 amps, and VD equals 0.56 volts. So basically, I've just taken the two graphs, superimposed them. This was 1 and 1 prime rather, and the nonlinear one was related to equation 2. So before I jump off to one other thing, define something for you. Notice this curve here. Okay, this is a straight line that reflects the Thevenin constraint that I apply on my nonlinear device. And I mentioned earlier, we're going to do this again and again and again. I think you will see this at least 10 more times in this course, where I take a Thevenin equivalent of the following form, some voltage V, some R, and apply that in series across something interesting. And so this line that I see here is the constraint imposed by the Thevenin equivalent, and you can see that from the equation 1 prime. Now, so there's a name for this line. So this line is called the load line. Okay, you will see more reasons for this later, but this line is called the load line. Let me show you one other little trick, just in case you didn't completely get how I solved the graphical method. But one little trick here, if you like PowerPoint, you will enjoy this. And if you don't like PowerPoint, you will hate me for it. So if you look at these curves, I have my two equations in ID, the 1 prime and 2, and I've plotted them for you here. Okay, on the left-hand side, I plotted equation 2, right-hand side, I plotted equation 1. And fundamentally, all that the graphical method is doing is simply superimposing the two graphs, and by superimposing the two graphs, it is finding the point where the two curves intersect. Okay, and this is what you get. Okay, so let me do that again. So I take one of the curves and superimpose it on top of the other curve, given the same axes and the same scales for the axis, and then I go ahead and find the solution for the point where the two intersect.